Good morning, one and all. Today we are going to discuss finite state automata with epsilon moves. That means finite state automata. This is finite state automata means this is an NFA with epsilon moves. Here, unlike our non-deterministic finite automata without epsilon moves, here we have a special symbol called epsilon. Here these two are epsilons, and epsilon move means without reading any input it can switch states. That means from Q0 to Q1 you have an epsilon transition means without reading any input you can have a transition from Q0 to Q1. And without reading any input symbol you can have a transition from Q1 to Q2. That means without reading any input symbol you can switch from Q0 to Q1 as well as Q1 to Q2. That means empty string can be accepted in this case because without reading any input it can switch from Q0 to Q1 and Q1 to Q2. That means without reading any input symbol it can switch states, and those kind of transitions are called epsilon transition. But this is directed. That means from Q1 to Q0 you cannot have epsilon transition. Once you have an epsilon transition from Q0 to Q1, you can switch only from Q0 to Q1. Okay. Now this is an example of LDC. This the language accepted by this is a number of zeros, and after that it will switch to Q1, and 0 or more number of ones, then after that it will switch to Q2, and here you can have any number of 2's. That means here 0 or more occurrence of 0 followed by 0 or more occurrence of 1 followed by 0 or more occurrence of 2. That means, for example, 0, 1, 2. This is a valid input symbol. Why? That means 0, then reaches here 1, after that reaches here, then 2. Okay. In the case of 0, 1, 2, 2, 2, 0, that means a single 0. After that 1, that means without reading anything after 0, it will switch to Q1. Then it is accepting 1, and after that it reaches Q2, and after that you have 1, 2, 2, 2. That means that can be accepted. But see, suppose that after that there is a 1. 0, 1, 2, 2, 2, 1. That means there is no way, once it reaches Q2, there is no way to return to Q1. That means this cannot be accepted. If you have 0 here, what will happen? That means that won't be accepted. That means a number of zeros followed by a number of ones followed by a number of 2's. Okay, so that is the language accepted by this. That means any string 1, 2 is also valid. By that means here without reading any input symbol it reaches Q1. After that a single one. After that it reaches here 2. That means 1, 2 is possible. Simply 2. That is also possible. And this is a non-deterministic finite automaton with epsilon moves. So now again it's a 5 tuple Q sigma delta Q0 F. Q is a set of states, sigma is the input alphabet, delta is transition function, Q0 is the start state, and F is a set of final states. See here delta, the transition function, is a mapping from Q cross sigma union epsilon. That means in addition to the input symbols you have an additional symbol. That means sigma union epsilon. You are going to have a new input symbol which is called epsilon, and there is a mapping from current state Q to 2 raised to Q. That means the power set of Q that we have already discussed. And in the case of NFA, this is Q cross sigma to 2 raised to Q, and here in this case Q cross sigma union epsilon to 2 raised to Q. Okay. Now we are going to have epsilon closure. That means the epsilon closure of a set of a state Q. Epsilon closure of a state Q is defined as the states which can be reachable, the set of states reachable from Q through epsilon transitions only. Okay, that means here from state q0, that means if we are going to calculate the closure, epsilon closure of q0, from q0, epsilon closure of q0 contains q0 itself. If any state is contained in its epsilon closure. Epsilon closure of q contains q. Okay, that means epsilon closure of q0 by default it contains q0, and q1 and q2 are reachable from q0 through epsilon transition solely. That means from q0 you can reach q1, and from q1 you can reach q2. That means from q0 to q1 there is a path having only epsilon transition. From q0 to q2 also you have a path labeled epsilon only. That means from q0 to q1 to q2. That means epsilon cluster of q0 contains q0, q1 and q2. What about epsilon cluster of q1? Epsilon cluster of q1 contains, by default, q1 is a member of epsilon cluster of q1. Okay. Now from this q1 you can reach q2 only using epsilon transition. That means q1 and q2 are members of epsilon cluster of q1. Now what about epsilon cluster of q2? Epsilon cluster of q2 contains q2. That is by default epsilon cluster of q contains that state itself. Now our delta, the transition function, is a mapping from q cross sigma union epsilon to 2 raised to q. Now we are going to extend delta to q cross sigma star. That means here we have defined, for example, you have delta of q0 on 0, delta of q0 on 1 like that. That means delta is a mapping from q2, that means the state to some transition, that means some input symbol. Okay, now we are going to extend this delta to q cross sigma star, means that is called delta cap. That means you can have a statement like, you can have a transition like, say, delta cap of q0 That means instead of putting a single 0 or single input symbol here, you are going to have a string here. That means that is why you have delta cap. That means as parameters of delta, you can have only a single input symbol, whereas in the case of delta cap, here you have a string. That is defined as delta cap of q0101. That means we are extending delta to q cross sigma star. That means delta cap of q0 epsilon. What will happen? Delta cap of q0 on epsilon. We are extending this to delta cap on q0 epsilon is epsilon closure of q. Delta cap of q on epsilon. This is simply q. The definition is delta cap of q epsilon. That means without reading any input symbol, epsilon closure of q contains q. And likewise, delta cap of q epsilon is defined as epsilon closure of q. That is delta cap of q WA means, here WA is a string. That means WA is the string. This is the string WA. That means here you have a number of symbols in it. That means initially, before processing this W, the finite control is in state Q. That means this is not a single state, it is a set of states. And before processing this, this is the finite control is in a set of states Q. And after processing W, suppose that it reaches R. It reaches R is also a set of states. R is also a set of states. And it after reading A, suppose that it reaches P. That means here R is also a set of states. And when this set of states receives A, suppose that it reaches P, then you have to take the epsilon closure of P. Then you have to take the epsilon closure of P. So that is the definition of this. That means delta cap of QWA is defined as the epsilon closure of P. That means here suppose that initially this is in state Q. That means before processing this WA, which is a string, suppose that this is in state Q, and after processing this, suppose that it reaches a state P, and P is defined as P for some R, in delta cap of QW. That means you are applying this delta cap to QW, then it reaches a set of states R, and delta of RA contains P. That means after, that means you are going to have delta cap of QW is equal to what? R. Delta cap of QW, that means after processing this W, suppose that it reaches a set of states R, and after that you are applying this A, or if the input symbol A is accepted, then these are a set of states, and all these states will switch to new states, and you have to take the epsilon union of the epsilon closure of all these, that is P. Okay. That is the definition of this. When you are doing an example, you will be aware of this. Okay. Then this is the definition. Delta cap of QWA. That means I will show you that this is W and this is A, and initially that will be in state Q. After processing this, it will be in state R. And after processing this, that will be in state P. And the definition is delta cap of QWA is equal to epsilon cluster of P, where P is equal to the set of states P such that for some R in delta cap of QW, that means delta cap of QW is equal to R. Delta of RA, that means again if it is accepting one more symbol A contains P, then you have to take the epsilon cluster of that. When you are discussing or doing problems related to this, you will be better aware of this. Okay. Then, what is language accepted by M? What is the language accepted by M? That is defined as W such that all the strings W such that W is an element of sigma star. W is an element of sigma star means W is a string derived from one or more symbols of sigma, and delta cap of QW contains a state from F. That means if you after processing QW, you reaches a set of states R, and any one of these states, that means R is a set of states, and in that set of states any one of that is a final state, that means that can be accepted. That is L of M is equal to W such that W is an element of sigma star, and delta cap of QW contains a state from F. Okay. Then regarding this example, what is delta of Q0 on 0? Delta of Q0 on 0 is Q0 itself. Then what is delta cap of Q0 on 0? Delta cap is having another definition. That means delta cap of Q0 is what? Delta of Q0. You have to take delta of Q0, which is Q0, then take the epsilon loss of that. That's why you have delta cap of Q0 equal to epsilon loss of Q0 equal to Q0, Q1, Q2. Q0, Q1, Q2. Now, what is delta cap of Q0 on 0, 1? What will happen? Delta cap of Q0 on 0, 1 is epsilon cluster of delta of, that means delta is defined for a single input. Delta is defined for a single input, and delta cap is defined for a string. And delta cap of Q0 on 0 is epsilon cluster of delta cap of Q0 on 0. That means here 0, 1 means here suppose that this is 0 and this is 1. That means initially this will be in state, what state? In state Q0, and after reading 0, what will happen? Delta cap of Q0 on 0, what is that? Delta cap of Q0 on 0 is defined as delta of Q0 on 0 you have to find out delta of q0 10. What is delta of q0 10? Delta of q0 10 is q0 and take the epsilon loss of that. That is q0, q1, q2. So actually here this is q0, q1, q2. q0, q1, q2. This is R. Okay. Then q0, q1, q2. That means delta of q0, q1, q2. And after that you are going to apply 1. That means what is q0 on 1? q0 after accepting 1, it is epsilon. And what is q1 on 1? It is q1. q1 and what is q2 accepting 1? That is 5. Okay, that means this also is 5. Then take the union of this q0 on 0 is 5. 5 q1 and 5. That means it is q1 and that is it is q1 and take the epsilon loss of q1. That means take the epsilon loss of q1, you get q1, q2. You get q1, q2. That is delta gap of q0 on 0 is q1, q2. Okay, and we have the definition of delta of RA. That means R is actually it's a set of states. Delta is defined for a set of states. R is a set of states. In the case of DFA, here this is an NFA. In an NFA, you have a set of states defined by R and union of Q element of R means here this R is having a number of states and delta of RA is defined as the union of delta of QA. That means it is a union of Q element of R. That means this R is having a number of states and for each state you are going to apply this A. Apply this A and take the union of all this. That is the definition of this. Then what is delta cap of RW is defined as, again it is taking the union of Q element of R. Suppose that this R is having Q0, Q1 and Q2. Then you have to apply Q0 on W, delta cap of Q1 on W, delta cap of Q2 on W. Then take the union of all this. So in that way, we can, this is the definition of delta and delta cap. Okay. We are going to discuss how an NFA with epsilon moves can be converted to an NFA without epsilon moves. Now, this is an NFA with epsilon moves and we are going to have a replica of the number of states. That means Q0, Q1 and Q2 is the final state and we are having the double circle. Now this is the start state and from Q0 to Q. See here upon receiving a 0, what are the states it can reach? Here from state Q0 on reading 0 it can reach that state. Okay. And once you are here means you are here and here. Okay. That means you are here means you take the epsilon loss of that. That means Q0 accepting 0 is staying in the same state and once you are in state Q0, that means through epsilon transition you can reach Q1 as well as Q2. So you are going to have 0 transition to Q1 and you have a 0 transition to Q2. That means once you are in state Q0 and if you are accepting a 0, after accepting a 0 it can be in the same state and after accepting a 0 it can switch to Q1. Why? After accepting the first 0 we are in state Q0 means and at the same time we are in Q1 and Q2 because epsilon plus of Q0 contains Q1 and Q2 also. Now you are in state Q0 means upon receiving 1 what will happen? You are in state Q0 means you are in state Q1. Why? Epsilon loss of Q0 contains Q1. That means you are in state Q0 means you are in state Q1 and upon receiving Q1 after receiving 1 it is taking the same state Q1 there. So you have a transition from Q0 to Q1 labeled 1. Why? You are in state q0 means you have an epsilon transition to q1. You are in state q0 means you are in state q0, q1 and q2 at the same time. You are in state q0 means as it is having as the epsilon velocity of q0 connects q0, q1 and q2. You are in state q0 means you are in state q0, q1 and q2. Okay. So if it is accepting 1, what will happen? Epsilon velocity of q0 contains q0, q1 and q2. q1 accepting 1, it is staying in the same state q1. That means you have a transition from q0 to q1 labeled 1. So I am going to have 0, 1. That means upon receiving 0 and 1, it can switch to q1. Okay. Now see, once you are in state q1 means you are in state q2 because epsilon velocity of q1 contains q2. So after accepting that 1, you are in state q1 means you are at the same time you are in state q2. So we are having an arc labeled 1 to q2 also. Okay. Then now if q1 is accepting 0, q1 is accepting 0, that means what about this one accepting 2? That means here we have sigma, that means the input output is having 0, 1 and 2. So here we have considered what is 0. After accepting 0, it can either stay in the same state q0, q1 or q2, and in the case of 1, it can either switch to q1 or to state q2. And now if it is accepting 2, what will happen? You are in state q0 means you are at the same time you are in state q0, q1 and q2 because the epsilon velocity of q0 connects q0, q1 and q2. Among that, q2 can accept 2. After accepting 2, it is staying in the same state. So here from q0 it can accept 2 also. From q0 it can accept 2 also. But on accepting 2, it cannot switch to state q1. Why? q0 cannot accept 2. q1 also not able to accept q2 2, but q2 can accept 2. But once you are in state q0 means you are in state q0, q1 and q2. Why? Epsilon velocity of q0 contains q0, q1 and q2. Now you are upon receiving 2, what will happen? It is coming back to or it is going to state q2. So in state q0, that means you are in state q0 means you are at the same time you are in state q0, q1 and q2. Then what is delta cap of q0, q1, q2 on 2? This is delta of q0 on 2, delta of q1 on 2, delta of q2 on 2. That is delta of q0 on 2 is 5, delta of q1 on 2 is 5, and delta of q2 on 2 is q2. Then take the epsilon velocity of q2. Then that means it is to q2. That is why you have an arc from q0 to q2 level 2. Okay. Now what about the states of q1? q1 cannot accept 0. So q1 on accepting 0, it's f5. q1 on accepting 0, it's f5. And q1 on accepting 1, what will happen? Is staying in the same state. And once you are in state q1 means you are at the same time in q1 and q2. Why? Epsilon velocity of q1 contains q2 also. q1 and q2. Then after reading 1, take the epsilon velocity of q1. That means it can switch to q2 also. Because you are in state q1 means you are at the same time you are in q1 and q2. Okay. So q1 on 1 is what? q1. You are in q1 means you are at the same time in q1 and q2. Why? Epsilon velocity of q1 contains q1 and q2. So that's why you have an arc label 1 from Q1 to Q2. Now, what about 2? What about 2? On input 2, you are in state Q1 means you are at the same time in Q1 and Q2. So Q2 accepting 2, what will happen? It is staying in the same state. So you have an arc label 2 from 1 to 2. Okay. So as far as Q1 is concerned, it is accepting two inputs 1 and 2. And now we are moving to state Q2. In state Q2, epsilon class of Q2 contains Q2 only. Then you have 2 here. Okay. So in that case, epsilon class of Q2 is Q2 only. Then Q2 is having Q2 cannot accept 0 as well as 1, and can accept only 2. This is the way we are converting a finite state automata with epsilon moves to, or an NFA with epsilon moves to NFA without epsilon moves. Okay. Now this can easily, so the table for this is NFA with epsilon moves is, here you have Q0, Q1, Q2. Here the inputs are 0, 1, 2 and epsilon. That means in an NFA with epsilon transitions, sigma union epsilon, sigma is 0, 1, 2. That is the permissible inputs, and in addition to that we have another input symbol epsilon. Then Q0 on 0 it is Q0, Q0 on 1 it's 5, Q0 on 2 it's 5, and Q0 on epsilon it is Q1. And Q1 on 0 is 5, Q1 on 1 is Q1, Q1 on 2 is again 5, Q1 on epsilon is Q2. What is Q2 on 0? Q2 on 0 it is 5, Q2 on 1, Q2 on 1 is Q2 on 1 again 5, Q2 on 2 it is Q2, and Q2 on epsilon is 5. So this is the transition diagram for NFA with epsilon moves, and when we are converting this, the transition table is like this. Again Q0, Q1, Q2. Here we have inputs 0, 1 and 2. Here these are the inputs, and Q0 on accepting 0 will happen. Can either stay in the same set Q0 or Q1 or Q2. That means here we have Q0, Q1, Q2. Okay. This on accepting 1 what will happen? It can move to either Q1 or Q2, and here we have Q1 or Q2, and on accepting 2 it is moving to Q2. That means here we have Q2. What about Q1? Q1 0 it's 5, Q1 on 1 it is Q1 or Q2, Q1, Q2, and Q1 on 2. Q1 on 2 is Q2. And Q2 accepting 0 what will happen? Q2 accepting 0 it is 5, Q2 accepting 1 it's 5, and Q2 accepting 2 it's Q2. So this is the transition diagram for NFA without epsilon moves. So this is converting this to this. Okay.